So we have looked at our first model of quantifying the option price, and this was the binomial model. However, we noticed that as the number of subperiods goes up, we have to rely more and more on numerical calculations, so the use of computers and a particular algorithm to actually price the options. And it would be much easier for us if we actually had a formula for option price that where we can directly plug in the inputs and get as an output option prices. But in order to progress there, we need to make a few more assumptions before we are in a position to actually look at such a formula. So the assumptions that we are going to make are the following, that we are going to assume that the risk-free interest rate and the stock price volatility are going to be constant over time and are not going to be changing from one sub-period to another. And we also saw that once we were dividing into more sub-periods, the distribution of stock price at expiration was looking something similar to the log normal distribution. So we'll go ahead with this assumption and take it to the limit. And when the stock price is exactly log normal, one can actually end up deriving a option pricing formula. And this is what we turn to next. So the Black Scholes pricing formula for a European call option for a stock which pays no dividend before option expiration is given by the following formula. So this is one of the most famous formulas in finance. So let's take a look first at what it says. This is a bit symbol heavy. So we have got C naught is equal to S naught ND1 minus X e to the power minus R capital T N of D2, right? So what are these symbols? We are going to go through them, but first note that this ND1 is basically saying that we are evaluating this function n at D1 and we are multiplying it by S0. So what is D1? D1 is also something which is going to be dependent on the inputs that we are putting. So D1 is the ratio of log of S0 by X plus R plus sigma square by 2 multiplied by T divided by sigma root T. And here the D2 that you see, that is again an input in this function n of D2, and that we are going to multiply by X into e to the power minus RT. So this D2 is basically the D1 that we have just calculated minus sigma times square root of T. So there are a lot of symbols here. Let's try and actually understand what each of these symbols stand for. So the C0 is obviously the current call option value. So this is something that we have seen before. S0 is again something that we have seen before as well. So that's the current stock price. And X is the exercise price. R that we see here at multiple places, e to the power minus RT, as well as this R here, represents the risk-free interest rate, which is stated in the annualized compound rate. Capital T that one sees here is the time to expiration for the contract. And this is stated in the form of years in this contract, in this formula. Sigma, again, that we see in here and in here, stands for the standard deviation of the annualized compounded rate of return of the stock, right? So that just leaves this N of D. So this N of D is a CDF, which corresponds to the standard normal distribution. And when we write N as a function of D, we are evaluating this CDF at a point D. So this formula looks like a handful. So what we are going to do is first we are going to just get a bit of practice seeing how to use this formula. And then we'll come back and talk a bit about an intuitive reasoning behind why the formula might look like this for a call option. So let's first use an example to see how to use this formula. So we have got that we want to figure out what's the price of a call option in the following scenario. So you're given some inputs. So you're given, for instance, that S0 is 100. So the current stock price is 100. You're given X equal to 95. So the strike price of this option which you want to price is 95. Then you are told that R is 10% or 0.1. So what was R? This was the risk-free interest rate stated in the annualized compounded rate way. Then T is 0.25. So remember, this T is actually time to expiration in years. So 0.25 years basically means 1/4 of a year or 3 months, right? So if you are given information in months, let's say 6 months, that would correspond to T equal to 0.5. So you have to convert the months into years. And sigma is equal to 50% or half, and that represents the standard deviation of the annualized continuously compounded rate of the rate of return of the stock. So basically, we are given these inputs, and now we want to apply this formula, right? Now, in order to apply this formula, we basically need to know what D1 and D2 is. So first, we need to evaluate D1 and D2. We can see that D1 itself is a input in D2. So we should start with actually evaluating D1, right? So D1 looks like this, and we have all the ingredients, right? We know what S0 is, we know what X is, we know what R is, we know what sigma is, we know what capital T is. So all these are information are given to us. So we are just directly plugging in these things. So we end up getting that D1 is log of 100 by 95. So this is S0 by X plus R was 10% or 0.1. So you have to plug this in decimal form. Plus you have got sigma square by 2. So sigma was again 0.5. So 0.5 square by 2 multiplied by T, so which is 0.25. And in the denominator, you have got again sigma, so 0.5 multiplied by square root of T, right? So if you plug in all these things, you end up getting a numerical value for D1, so which here is approximately 0.43, right? So that's the first point that you have. And once you have D1, you can use this as an input in the formula for D2, right? So D2 is 0.43 minus sigma 0.5 times the square root of 0.25, right? So that also gives you a value of D2, right? So now we are in a position to actually approach the formula for the call price itself. So we have just evaluated D1 and D2. We need to know what's the CDF of the normal distribution at D1 and D2. That's the other next thing step in our process. And this you can do either using the normal distribution tables or software. So these are things that are easily available in Excel, R, and so on, right? So the CDF of the normal standard normal distribution at 0.43, for example, is going to take the value 0.6664, and the CDF evaluated at 0.18 takes the value 0.5714, right? Okay, so now we know what this n of D1 is. We know what this n of D2 is. And S0 is given to us, X is given to us, R and T are also given to us. So we can plug all of that here, right, in the formula. And so therefore S0 was 100, n of D1, we have just calculated this to be 0.6664, right? X was 95, R was 0.1, T was 0.25, and n of D2 again we calculated to be 0.5714. So we can just plug this in and get 13.70, right? So this is a pretty straightforward formula. The process. So you have to kind of like just follow it systematically, and you have to make sure that you are inputting these numbers correctly in the correct form. So for example, you should not input R equal to 10 here, but 0.1, and sigma should not be 50, but 0.5, and T should be in years and so on. And then just systematically first evaluating D1, then D2 based on that. Then you calculate what n of D1 and n of D2 is, and then you are in a position to directly apply it to the call option, right? And this is what you end up getting. Okay, let's now try and understand a bit behind why this formula is looking like this, right? So this is the formula that we have stated, right? And one way to go about thinking about how to interpret this formula, and this is going to be just a bit intuitive because we do not have the mathematical tools to get into details of how this formula is derived. So this is just to give you an idea. So think of these two ND terms that you see here as basically the risk-adjusted probability that the call option is actually going to expire in the money, right? So remember, expire in the money means that you will execute it once at the expiration date, right? That's the idea. So if you have got that both of these ND terms are close to 1, which means that you are basically certain that the call option will be exercised, right? Then the call option value itself is going to be equal to almost, if you put these terms to be equal to approximately equal to 1, you end up getting that C0 is going to be S0 minus X into e to the power minus RT, right? Now, this term should look familiar. This is nothing but S0 minus the present value of the strike price. And this is the adjusted intrinsic value that we had discussed before, right? So what's the interpretation in this scenario? That if you are certain that the call option is going to be exercised, right? Then this is as if you are basically owning a claim on a stock, right? Which again has a current value of S0, and you know that in T amount of time you're going to be paying out X, right? So which is the strike price. So therefore, from today's perspective, this is the present value of X, right? And so that's this term that you see here, right? Why is it looking like this type? Because this is the continuously compounded version, right, of the present value of X. Remember, if it was discrete, you would have done X by 1 plus R to the power T. If it's continuous, the way you discount this X to arrive at the present value is that you multiply it by e to the power minus R capital T, right? And so that's why the formula is looking like this when you have got this n of d terms both being very close to 1. Let's take the other extreme case where you've got both of these ND terms as being close to 0. So in this scenario, think of this as the one where we are saying that the option is not likely to be exercised. So again, this was the formula. And if you have got both of these ND terms to be equal to 0, then C0 is actually close to 0 as well, right? So this is basically saying that if you do not anticipate that the option is going to be exercised, then the value of this call option should also be close to 0. Right. So these are the extreme cases. What happens in the middle values of ND? So then you can interpret this call value as the present value of the call's potential payoff, where you adjust for the probability of the in the money expiration, right? So these are the probabilities that you're adjusting. So that's why this is the price of the stock today, but you are adjusting for the fact that you will actually kind of exercise this option. So this is ND1. And similarly, you are at, this is the present value of the strike price. And again, you are adjusting this by N of D2. Okay. So why can these ND terms be interpreted as probabilities? Again, we do not have the necessary mathematical tools at this point to answer this question very precisely, but we can get a rough idea of what is going on. So if you go back to this D terms, we see that this has this log S0 by X in the numerator, and then it has this sigma by root T in the denominator, right? So what are these terms actually signifying? So you've basically got log of S0 by X. You can think of it as approximately the percentage amount by which the option is currently in or out of the money. So for instance, suppose that S0, the current stock price is 105 and X is equal to 100, then this option is actually 5% in the money, right? Because this is just 5% more than that. So in this case, if you had calculated log of S0 by X, you would have got actually 0.049, which is close to 5%, right? And on the other hand, if you had instead S0 is equal to 95 and X equal to 100, so that the option is out of the money, then again, this is the option being 5% out of the money. And again, if you calculate this log of S0 by X, you end up getting something which is close to negative of 5%, right? So this is telling us that this first term log of S0 by X, that closely corresponds to this percentage amount, right? Okay, why do we have this denominator as sigma root T? Because this is roughly speaking, again, adjusting the amount by which the option is in or out of the money. So this was the numerator for the volatility of the stock price over the remaining value of the option. So this is the remaining time of the auction. and this is the volatility of the underlying stock, right? So basically, what this is saying is that higher the volatility stock, that's going to actually have effect on whether the fact that you are currently in or out of the money, is that going to extend to at the time of the expiration period, are you still going to be in or out of the money, right? So an option in the money by a given percent, which is the what you can think roughly as the numerator is saying, is more likely to stay in the money if both the stock price volatility and the time to expiration are low, right? So this is if both of this sigma and t are low, then this whatever is the numerator is saying, that's likely to kind of like continue to be in the right thing. Otherwise, this would actually be flipping if the volatility is goes up and so on, right? So this says that basically n of d1 and n of d2, both of them increase with the probability that the option will expire in the money. So this is again a very rough explanation. Again, one needs to pick up a bit more tools related to stochastic differential equation and so on in order to get a more precise explanation for these things. Okay, again, we have already mentioned in passing some of the assumptions we have made when we wrote down this formula, but let's mention the key ones. So one of the assumptions that we have made is that the stock is not going to pay any dividend until after the option expiration date. If the stock pays the dividend, then this is not the right formula and one needs to adjust it. And there have been scholars who have worked with coming up with formulas which takes into account dividends, but we are not stating it here, right? Again, we have assumed that R and sigma square are constant. There are more general formulas for Black Scholes where R and sigma square are explicit functions of time, and that has been incorporated. But here again, in the formula that we have stated, this is something that we are abstracted away from. And another assumption is that the stock prices are continuous. So what that means is that we are not allowing for jumps in stock prices to take place. Again, there have been kind of like research done on that to see how to incorporate those things. The other thing to note here is that you have got as input when you are using this formula several things, right? We have discussed this kind of like things that we have here, right? So a lot of these things can be easily made available, right? So you can easily see what the current option value is. You can see what the current stock price is. You can see what the exercise price for that auction is. And you can also figure out what's going to be the risk-free interest rate at that time, right? You need to look at a similar safe asset with the same maturity period T, right? So the only thing that is not straightforward in the formula is this sigma, right? And so people have used a variety of techniques based on both historical data, simulations, and different models for this sigma to come up with an estimate for this sigma. So again, if you take a more advanced course, this is something that one will go into more details about how do you go into evaluating or estimating this sigma square actually. Okay, so we have stated the formula in terms of a call option. What happens if you want to price the put option? Well, here one can use the put call parity theorem, which we had discussed last week to derive the price of a put option. So there are two ways in which you can go about doing it. So first is that you write down the continuous compounding version of the put call parity theorem, right? So remember the theorem basically had that P0 plus S0 was equal to C0 plus present value of X. So that's what we have still have here. Now we are going to just move the S0 to the other side because we want to figure out what's the price of the put option. And here, because we are doing things in terms of continuous compounding and in continuous time, when we write down the present value of X, we should write down X into e to the power minus RT rather than X by 1 plus R to the power T, which was the discrete time version of the put call parity theorem that we had seen last week, right? So this is the same theorem, but here this is the continuous time version. Okay, so once you have figured out what are the different values of C0 using the original Black Scholes formula, you have X, R, T, and S0, you can figure out what P0 is. The other way in which one can actually use the Black Scholes formula is that directly put in what this C0 was right here and get an expression for P0, right? So if you do that, so this is basically the Black Scholes pricing formula for the European put option for a stock which pays no dividend before option expiration. So the same thing that we had before, except that instead of call, we have put. And you are basically just plugging in the Black Scholes formula for C0 here and simplifying. So you end up getting that P0 is x into e to the power minus RT multiplied by 1 minus n evaluated at D2 minus S0 uh, multiplied by 1 minus n evaluated at D1, right? So let's see an example of how to use this formula. So suppose that we want to consider the same situation that we had before. So S0 is 100, X is 95, R is 10%, T is 0.25, sigma is 50%. And we want to figure out what's the price of a European put option in this scenario. So we basically kind of like do the same thing as before. We calculate D1 and D2. So that's exactly the same as before, 0.43 and 0.18, and then you end up getting what is the CDF of the standard normal at those points. And you can then plug this in, right? So n of D1, remember, was 0.6664, n of D2 was 0.5714. So if you plug this in, as well as x equal to 95, r equal to 0.1, d equal to 0.25 in this formula, you can actually calculate what the put price is going to be worth, right? So that's 6.35. So there's another way you could have done the same thing. So remember, we had already calculated this C0 as 13.70. So you could have also directly put it in this formula here. So C0 is 13.70, X, is 95, R is 0.1, T is 0.25, and S0 is 100. And so therefore you have all the expressions here, and you could have calculated P0 here as well, right? So you don't have to separately actually memorize this formula. If you know the formula for C0, you can just use the continuously compounding version of the put call parity theorem to get the Black Scholes prediction for what the P0 should be. Okay, so that's the put option. Let's look at a couple of applications of this Black Scholes formula. So one of them is how do actually people use the Black Scholes formula. So often times it's not used in the sense of, okay, we are going to put in the inputs, so what's going to be the ideal option price. So often people actually observe what the option price is, right? And remember that what we had discussed is that apart from sigma square, all the other things can be observed as well, right? So it's only in the sigma square that one has to figure out a way of estimating it. So what market participants do is that they often use everything else apart from sigma squares, and this includes the price of the call option as inputs in the analysis, right? So they use this to back out what is called the implied volatility of the option, right? So what is the implied volatility? So this is the value of the standard deviation that would be necessary for the option price that one observes to be actually consistent with this Black-Scholes formula, right? So basically, you can go back here in the formula, and it's as if you know C0, you know S0, you know X, you know R, you know T. So the only thing that you don't know in this formula is this sigma, right? So then you numerically solve this equation for the value of sigma that is consistent with all of these equations holding together simultaneously. So there are tools that one can easily use, in fact, even in Excel, that will tell you how to solve for this sigma, right? So this you cannot use it as a closed form solution, but you can numerically solve it using a computer, right? And the value of sigma that one gets as a result of this exercise is basically the implied volatility. And then one can compare this with the actual stock standard deviation, right? And if the actual standard deviation exceeds this implied volatility, then people interpret this as thinking that this option is actually a good buy, in the sense that the observed price of the option is actually below the what should have been the fair price, right? So it's underpriced, and hence it makes a good idea to purchase this option. Okay, let's look at another application. So recall that we had discussed when we were thinking about how to compare options with stocks, we had kind of like this discussion before, right? So we had thought about what are the pros and cons of buying 100 shares or buying 1,000 call options based on those 100 shares. And we had seen this diagram before in the last week's lectures, right? So particularly we had compared this all stocks versus all options. And what we had come to the conclusion is that basically options are more sensitive in the sense that their rates of returns are more affected by changes in the stock prices, right? So that was like a qualitative discussion, and this is also a discussion based on some of the graphs. So then we want to come up with a numerical quantitative way of stating this, right? Because this is often you'll see useful when we are doing portfolio management. So how do we come up with that? Well, here too, the Black-Scholes formula can be used. But before we get into that, let's think about conceptually what we want to do. So we want to basically quantify how sensitive option prices are to the value of the underlying asset, right? That's the basic thing that we are looking after. And this can be done using the hedge ratio. So what is the hedge ratio? So this is the change in the option price due to 1 unit increase in the stock price, right? So based on this diagram, we already know that call option should actually have a positive hedge ratio. And in fact, a put option should have a negative hedge ratio, right? So why should a call option have a positive hedge ratio? So you can see here that as the stock price is going up, basically the call options rate of return is going up, and hence therefore its price should be going up, right? Whereas the put option, it's exactly the opposite relation, right? In fact, you can use the put call parity relation to think about why it should have a negative relation between the what is happening to the price of the call option and the price of the put option. So this hedge ratio is also sometimes known as a options delta, so something that you might hear. And how do we calculate this hedge ratio or delta? So one way is that if you have the graph, you can actually graph the option value as a function of the stock price. And if you look at the definition, this is nothing but the slope of this curve, right? The curve being the graph of the option value as a function of the stock price, right? So suppose that you do the graphing and you find that the slope of the curve is 0.5 at a particular stock price 110. So what this means is that if you increase the stock by 1 unit or one small unit, then the call increases by approximately 0.5 units, right? So the price of the call option. So this basically tells you that if you are selling a call option, then essentially you need for every call option that you sell, you need zero point 0.5 shares of stocks in your portfolio to hedge the price exposure, right? Let's understand why this is the case. So suppose that you had sold 10 call options and you are holding 5 shares of stocks in your portfolio to hedge this exposure, right? Now, suppose that there is a 1 unit increase in the stock price. Now, because you were holding 5 shares of stocks, this 1 unit increase in stock price will mean that there is an increase in your portfolio by 5 units, right? But you have also sold this 10 call options, right? And as a result of that, the price has actually gone up by zero point 0.5 units each. And so therefore you are kind of like basically suffering a loss of this 10 into zero point 0.5 or 5 units from your portfolio on that basis as well, right? So increase in 5 units by the stock price is actually exactly cancelled out by this loss on the call options by 5 units. So then therefore uh, you end up getting that this is exactly hedged, and therefore your total wealth is going to be unaffected, right? So this is what we mean by hedging the price exposure. Okay, so what's the significance of the Black-Scholes formula here? So the Black-Scholes formula can actually be used directly to calculate hedge ratios. So for a call option of the type that we have been studying, the hedge ratio is actually equal to N of D1. And remember, this N of D1 is basically CDF that we have been looking at, right? And so therefore, so this is going to basically lie between 0 and 1, right? Remember the properties of CDF. So this is something that always lies between 0 and 1. And so therefore, you know that the hedge ratio for a call option is always going to lie between 0 and 1. What about the hedge ratio for a put? Well, that's going to equal to ND1 minus 1, right? In case you ever forget it again, go back and look at the put call parity formula, and take a derivative with respect to S0 on both sides. So that will tell you how these two are related, right? Okay. So if n of d1 is lying between 0 and 1, so n of d1 minus 1 lies between minus 1 and 0. So the hedge ratio for a put is something which is negative, and the hedge ratio for a call is something which is positive. So again, intuitively, why should it be the case that the option value change is less than one for one with a increase in stock price? Well, let's think about it. If you have we are looking at call option first. So if you are having a call option and the option is very far in the money, in the sense that you are almost certain that this is going to be exercised, then an increase in stock price by 1 unit would have corresponded to a 1 unit increase in the option value, right? So this is the stock minus the exercise price. So if that is going up by 1 unit, that corresponds to a 1 unit increase in the option value. However, if there is some probability that the option will actually end up expiring out of the money, then you are no longer this 1-to-1 relationship holds true that 1 unit of increase in the stock price is going to cause 1 unit increase in the option value, right? So now 1 unit increase in the stock price is going to lead to some sort of a weighted average of zero and this 1 unit increase, and so therefore the ultimate payoff to the call is going to increase either by a smaller amount or by no amount as at all if we are in a state where we are certain that this is not going to actually expire in money at all, right? So that's how you can interpret this number one. Now, one question here is that are we not somehow contradicting ourselves? Remember that we had started out by saying that these options are actually disproportionately more sensitive to the stock price movements. And we have just found that this measure that we have come up with is that, 1 unit increase in the stock price is going to lead to less than 1 unit increase in the call option value, right? So that's not the case. Why? Again, remember that when discussing this option bounds, we had figured out that the call prices are actually lower priced than the stock prices, and hence the rate of return of the volatility of the options can still be greater, right? So let's take a particular example to see what we mean by that. So consider a situation where we have got that S0 is 110, the hedge ratio is 0.5, and the price of the call option is 5. Suppose that from here, we have got that S is increasing by 1 unit. So S0 goes from 110 to 111. So if the hedge ratio is 0.5, that means that this is going to lead to an increase in option price approximately to 5.5 from 5, right? So what's the percentage increase in option price? So it has gone from 5 to 5.5. So that's a 10% increase in the option price, right? Whereas what's the percentage increase in the stock price? So this has just moved from 110 to 111. So the stock price increase is actually much lower, right? So it's 0.91%. So this is more volatile in that sense. And you can also calculate the elasticity, which is the ratio of this percentage changes. So that would be around 14.14%, right? So that's even higher, right? Okay, so as we mentioned that hedge ratios are often useful in portfolio and risk management. So let's take a small example to see how it works. So consider two portfolios. One portfolio consists of 700 call options and 300 shares. So these call options are exactly written on these shares. And the other portfolio consists of 800 shares of the same company, right? And you know that at the current stock price, the hedge ratio is 0.5. So the question is, which of these two portfolios is more exposed to the stock price movements of the company? So you can see that the problem is that you have got this 300 shares and 800 shares. So those are comparable, but you have also got the 700 call options. So we need somehow a way of converting this 700 call options exposures into thinking about how much does that is equivalent to in terms of exposures of shares, right? And this hedge ratio actually gives you exactly the tool that is required. So a hedge ratio of 0.5 basically means that we can think of this 700 call options exposure to the stock price movement as the same as 700 into zero point 0.5 shares exposures. So that means you can think of this 700 call options as having similar exposure as 350 shares would have had. And so that's one way of converting it. So we basically end up that the first portfolio, you can think of it is equivalent in terms of this exposure to stock price movements as consisting of 650 shares, whereas the second portfolio is about 800 shares. So in that way, the first portfolio is basically less sensitive again in monetary terms to stock price changes, right? But that does not mean that the first one is less risky because of the reasons that we just discussed. So this would also mean that the first portfolio is cheaper because call options are, as we have mentioned, cheaper than the shares. And so therefore, it's possible that because the first portfolio is worth less, so it can have a greater rate of return sensitivity, right? So exactly the discussion that we had here, right? Okay, so these are some of the discussions, and if you are interested in more applications, I encourage you to take a look at these references that we have mentioned before. So most of our lecture was based on this first reference, but you can also look at our standard reference for more additional discussions as well as examples based on this concept. So these are the two references for this part of the course.